Hey everyone, and welcome. Today we are going to be cracking the code on some of the most fundamental building blocks in math: squares, cubes, and of course, their roots. Now, I know that might sound a little intimidating, but trust me, by the end of this, you're going to have some seriously clever tricks up your sleeve. Okay, let's just dive right in.
So, let's start with a question. What do a chessboard and a Rubik's Cube actually have in common? And no, this isn't a riddle. They're perfect, real-world examples of the mathematical powers we're about to explore. See, one lives in 2 dimensions, the other in 3, and they both hold the key to our entire journey today.
So we're going to start our dimensional journey in 2D with the simple, really elegant power of squares. This is the foundation for everything else we're going to cover.
So what even is a perfect square? Well, it's pretty simple. It's just the number you get when you multiply any whole number by itself. You can kind of think of it as a number expanding to fill a 2-dimensional space, creating a perfect square shape.
And in the language of math, it looks just like this: n times n, which we write as n with that little 2 up top, or n squared. It's clean, it's simple, and it's incredibly powerful.
For instance, 9 times 9 gives you the perfect square 81. Or 6 times 6 is 36, and 12 times 12 is 144. Each of these results, 81, 36, 144, they're all perfect squares because they come from a whole number multiplied by itself.
All right, so we know how to build a square, but what if we want to go the other way? Reverse the process? That's where square roots come in. It's all about learning to work backwards.
Finding the square root of, say, 36 is easy. It's 6, right? But what about a number like 300? It's not a perfect square. How do you even begin to figure that out without just reaching for a calculator? This is a really common sticking point.
Well, don't worry, there's a great little strategy for this. First, you just find the 2 perfect squares that your number sits between. So for 300, that's 289, which is 17 squared, and 324, which is 18 squared. Then you just figure out which one it's closer to. 300 is definitely closer to 289, so you know the root is going to be closer to 17. You could guess something like, 17.3, and then you can check it. It's a fantastic way to get a really solid estimate.
Okay, estimation is great, for sure. But what if I told you there's a brilliant shortcut for finding the exact root of a big number as long as you know it's a perfect square? This is seriously one of my favorite math hacks.
Check this out. This table reveals an incredibly powerful pattern. The final digit of a perfect square gives you this huge clue about the final digit of its root. So notice how some of them are paired up, right? A square ending in 1 means its root has to end in a 1 or a 9. If it ends in 4, the root ends in a 2 or an 8. Just noticing this is the key to the whole shortcut.
So let's take the number 784. It ends in a 4. We just look at our table, and that means its square root must end in either a 2 or an 8. This instantly narrows down our options and makes finding the root so much faster. And the answer, by the way, is 28. It's a perfect example of how powerful pattern recognition can be.
Okay, so we've pretty much mastered 2 dimensions. Now it's time to level up. Let's add that 3rd dimension and start talking about perfect cubes.
So if a perfect square is all about a flat 2D area, a perfect cube represents the actual volume of a 3D object. A cube. Makes sense, right? If the side length of a cube is n, then its volume is a perfect cube. And the math follows that logic perfectly. Instead of multiplying a number by itself just once, we do it twice. So n times n, or n cubed.
So, we can build the cube. Now, let's learn how to deconstruct it. It's time to crack the cube's code by finding its root.
You should think of the cube root as basically the undo button for cubing something. If you know a cube's volume, the cube root tells you the length of one of its sides. So, if 2 cubed is 8, then the cube root of 8 is 2. It really is that straightforward.
So you're probably wondering, we had that cool trick for square roots, so is there a shortcut for finding perfect cube roots as well? And the answer is yes. And believe it or not, it's actually even easier.
Okay, just take a look at this table. For cube roots, the pattern is even more powerful. See, unlike with squares, every single ending digit of a perfect cube corresponds to a unique ending digit for its root. A cube ending in 2 will always have a root ending in 8. One that ends in 7 will always have a root ending in 3. There's zero guesswork here. Let's try it with the number 2744. Okay, it ends in a 4. We just look at our chart, and a cube that ends in 4 must have a root that also ends in 4. From there, we can pretty quickly figure out the answer is 14. Just like that. No ambiguity, just a straight-up answer.
All right, you've learned the codes for squares and for cubes. Now it's time for a final challenge to put all this new knowledge to the test. You ready?
All right, here's a quick question for you. Looking back at those patterns we saw, which of these digits can never be the last digit of a perfect square? Is it A, 1, B, 4, C, 8, or D, 9? Go on, take a second to think about it.
And the answer is C, 8. This is a fantastic little rule to remember. A perfect square will never, ever end in a 2, a 3, a 7, or an 8. So if you see a big number ending with one of those, you know instantly it's not a perfect square. Pretty cool, huh?
Okay, let's try just one more, but this time we're going to work backwards. The question is, if the square root of a number ends with the digit 9, what's the last digit of the original perfect square itself? You can even look back at that first table if you need to. I'll give you a second.
Did you get it? The answer is 1, because a root ending in 9 always comes from a square that ends in 1. And we'll end with this really interesting thought. Between any two consecutive squares, there's a predictable number of non-perfect squares. The formula is always 2n. So, what is this rule and all the others we've learned today? Tell us about the hidden order and the beautiful patterns that exist just beneath the surface of our entire number system. It's something to think about. Thanks for joining me on this one.